Oh, I have only floating inductor only. Okay. Simulator. But let's talk about the floating inductor first. Yeah, floating inductor can be, yeah, this is a grounded inductor, right? One node is connected to ground. Yeah, floating inductor is, say, gyrator notation is this one. Yeah, this is my gyrator. Now it has some polarity, right? Oh. Some polarity, GM1. Then this means, see, if I have something like, if I put current polarity like that, then let's just see, what's my gyrator? Yeah, then this I1, I2 should be something like, is this correct or not? GM1 minus GM1, 0, V1, V2. Is this correct? I1 equal GM1 V2. Yeah, I think that's good. I2 equal minus GM1 V1. Okay, I think this is correct. So if I change this polarity I2 there, in this way, this should be positive, right? Okay? Because I changed the I2 by minus I2, okay? Okay, so here's, we already saw that if I connect a capacitor here, and this is GM1, so let's just say I have something like that. This is I1, I2. Then this one is a grounded inductor. Say L equal GM1, or actually GM1, I use two, sorry, the other way around. So we could implement this gyrator by GMC. So how does it look like? So by this polarity, I must put positive sign here, okay? You know, this is my V1. And then this is V1, this is I1, and then this is grounded, eh? Okay, then, so this is V2, and this is I2. Is this I2? Yeah, I2. Oh, let's see. Then this thing is connected to minus input, right? So this is GM1, the same GM1. Yeah, this is my gyrator, okay? Yeah, if I put two gyrators in series, like I have one gyrator here, yeah, it goes this way, GM1, okay? And then I have another gyrator there, the same thing, GM1. If I put a floating grounded capacitor there, yeah, they are all grounded. Then, this is V1, I1, V2, I2, then it becomes a floating inductor. Okay, so I used the same gyrator. Okay, the same gyrator. Let us see, is it working or not? Yeah. So let us see. So I need to calculate I1, I2. I1, I2 should be the same, right? So in this right-hand side model, see my I1 must be same as I2, and should be it's something like that, right? Okay, it must satisfy this equation, right? Yeah, let's look at the this circuit. Let's see. Okay, so this is what's this current? This current should be, oh, is it? Let's look at this one. What's this current? Oh, yeah, this current is only GM times V1. Is it right? Yeah, GM times V1. Okay. Yeah, this current is GM times V1. And then what's this current? That current is I1 here, right? Which is GM times V2, okay? This current is GM times V2. And then what's current flowing into this capacitor? Let's just say, this is Vx, right? Okay, so this is Vx. What's Vx? My Vx is just 1 over SC times the current. Current is only GM1 V1 minus GM1 V2, okay? Then what's I1? Yeah, my I1 is just GM1 Vx, right? Okay, what's my I2? Yeah, my I2 is GM1 Vx, right? Oh, that's good. And then, so I substitute this Vx there. Then this is I1, I2 equal 1 over SC GM1 square times V1 minus V2, okay? So if I compare this equation with that equation, so my inductor is only C over GM1 square, right? So I achieved my floating inductor. Question? No? No question? All right, no question then. Okay, let's look at the, oh yeah, this is the implementation of a floating inductor. I have a V1 here, and then V2 there. You can see this is a gyrator. Say, because the direction of a transconductor is here. This is somehow GM2, GM1. So I just make simplicity all GM1, all GM1, GM1, GM1. If this is a GM1, GM2, GM1, say, then my inductor is a C over GM1, GM2, okay? But for simplicity, we just put GM1. Then you see, this Vin is connected to positive input node, right? This Vx, actually, this is Vx. Vx is connected to minus input node, right? So here, see, this Vx is connected to plus input node, right? Although it changed the position. And then this V2 is connected to minus input node. So this is another gyrator in this direction, okay? GM1, right? The same, exactly same gyrator, in the same direction, okay? Yeah. So to implement the inductor of 0.159 Henry, then if we assume this capacitor is the same 7.96 nanofarad, the same grounded capacitor, CP1, CP3, then my GM1, GM2 is calculated to be 0.224 millisecond. I mean millisiemens. Okay. Yeah, this is that netlist. So I have a gyrator N1 and N2. So this gyrator thing is just this one. This is a grounded, one-sided grounded. So this is N1 and N2. So my GM goes from N1 to N2. Okay. So it says, what is this thing? 1M. Oh yeah, this is. This is only. You can see this is a gyrator. This is a transconductor. Yeah, this current. This transconductor 0 to N2, right? 0 to N2. Say current flows from ground to N2 node, right? Like that. Then this is 1 millisiemens times VN1. Actually, this is VN1, right? N1 0. This is a controlling branch. This is a controlled branch. So this is the G1. And then what's G2? G2 current flows from 0 to N1. Okay. Yeah, and then so this N2 is connected to minus input node, right? So this current is minus 1 GM VN2 because this is 0 minus VN2, right? So this is my gyrator, okay? Then see, I put my gyrator here. See, this is my gyrator N1. This thing becomes NX this time by this sub-circuit expansion. NX, this is NX. And then this NX ground, I put a grounded capacitor of, this time this is 1 microfarad. How come? 1 microfarad. Yeah, 1 microfarad. And then let's just see, there is another gyrator here, X2 gyrator, right? And X2, N2. Is it N2? Yeah, N2. And then this goes in the same direction, okay? This is 1 millisiemens, right? Same direction from NX to N2. And then I put current source here, AC1. Oh yeah, somehow I put current source there. Huh? Say this current source is 0 to N1. Oh yeah, I put current source here, AC1. This is 1 exponential j omega t. Okay, this current is applied there. And then I have another current. This is N20. I have another current there, N20. Okay. This is another AC1 current. So current flows in. I want to watch the voltage drop between N1 and N2. Okay. Then, say for that purpose, I used a voltage controlled voltage source. I generate N12. Say what's N12? This is N1 minus N2. Oh yeah, it's easy. So N12 node, I have a voltage controlled voltage source which gain is 1, Vn1 minus Vn2. So if I watch Vn2, which is a voltage drop between N1 and N2, right? Yeah, this is Vn1 minus Vn2. So sometimes I need, caution is I need a dummy resistor. See, if my input is 0, those nodes are floated DC, so I used a huge resistor there at every output node. Huge resistor. It doesn't affect the circuit performance. Okay. So for DC wise, some problem. I put there, all 3 points. Okay. Okay, let's try sigma spice here. Oh yeah.